What's up, everybody? Welcome back to Nuclear Barbarians. This is your weekly installment with me, your nuclear barbarian, Emmett Penny, and I am here with Jonah Messinger, who I found out about through the Breakthrough Institute. He's written a bunch of stuff I liked, including you wrote some awesome pieces about the Palisades closure
Thank you.
and what it would do. That I thought had some really important visuals in it and made some very important points. And now you have written a hot take on cold fusion. And I wanted to have you on because I don't know anything about this stuff and I want to know more. And it seems like a fascinating case to me. But before we get into the nitty gritty of that, dude, who the hell are you? How'd you become a guy that writes for Breakthrough, works on cold fusion stuff, all of that? Give me the rundown.
Yeah, well, first of all, thanks for having me on, Emmett. Big fan. Yeah, I mean, I don't know how far back to go, but yeah, like I sort of started working on like clean tech just out of high school basically, and I was working on solar policy, and then I went and worked on some solar cell stuff at the National Renewable Energy Laboratory. Um, and I did my undergraduate degree in physics and done my master's in energy at the University of Illinois at Urbana-Champaign. And after sort of my undergrad, I knew a PhD was in my future, but I wasn't quite sure sort of when to do that and when the right time was. And I found the Breakthrough Institute, and I sort of always known that um, while an environmentalist, I sort of felt a little bit out of place in
Mhm.
some sort of conventional environmental thinking. And I had sort of seen this fellowship that the Breakthrough Institute was offering, the Generation Fellowship, and it really appealed to me. And I think some of the work that Breakthrough had done really appealed to me. And so then I went and joined as a Generation Fellow, and then as a full time analyst, and did work on advanced nuclear, Palisades, Diablo Canyon, sort of um, a bunch of different energy things over there. And then I moved and started my PhD at the University of Cambridge at the Cavendish Laboratory in Physics. And I sort of still write for Breakthrough on the side. And I suppose I should mention sort of what Breakthrough is all about. So we're an
Mhm.
eco-modernist think tank, nonprofit. And basically, I would sort of boil it down to sort of two core beliefs. The first is technological solutions to environmental problems. And then the second is that we believe in sort of a dual future of flourishing for both humanity and ecology.
Mm, love that. And for people who want sort of like an overview of the breakthrough shtick, you can check out my interview from a few weeks ago with your colleague, Alex Trembath, who was fantastic, as he always is, when I had him on. But for now, we are going to turn our attention to fusion runs hot and cold, how the Academy has gotten cold fusion wrong for 3 decades. Um, I love that subtitle. I was immediately like, I don't even know what's about to go on here, but I want to talk to this guy about it. Because as we were saying before I hit record, being a nuclear advocate, I've become sympathetic to things that people are like, no, that's crazy. That'll never happen. Or like, that's a bad idea, and then you go back and you're like, oh no, there's a case here. The only difficulty I have with is that I'm not a stupid guy, but I am a dumb guy. And I don't know what is going on with the technical stuff. And so I was like, this is such a huge opportunity to get to learn about like this whole new energy vista. So let's start with a really basic question before we get into how we've neglected this tech for 3 decades. And it is, what is cold fusion?
Yeah, it's a good question. I think maybe the first thing to say is that cold fusion is sort of the original name, but it sort of evolved over the years, and I think maybe a better pedagogically sort of more instructive name is low energy nuclear reactions. And there's a number of reasons
Mm,
why that is, but one of them is that it might be the case that not only fusion is happening, but other nuclear reactions as well. And I think before we jump into fusion, it's probably worth mentioning just sort of like a brief bit about fusion itself. Um,
totally. I'd love that.
so, I mean, functionally, you know, elements are made up of mass, but the mass is mostly at the center. mostly at the center of the atom, the nucleus. And you've got protons and neutrons, and that's where the mass is. And protons being positively charged particles, they don't want to come together. It's sort of like taking two positive ends of a magnet and trying to push them together. They're going to repel each other. We call that Coulomb repulsion.
Mm.
But what binds these nuclei together is a force called the strong nuclear force. And it's much, much stronger than that repulsion at short distances, very close distances. And so that's what keeps this nucleus together. And if you were to take two nuclei and try to push them together, like we do in fusion, they're going to repel each other because you've got two positively charged nuclei that are going to try and not come together until you get really, really close. And at that point, they'll fuse for that same reason, the strong nuclear force. And so basically, conventional fusion, the whole idea is, well, how are you going to sort of overcome that repulsion, that Coulomb repulsion? And the answer is higher temperatures. Put a bunch of kinetic energy into the system, and eventually, as you get to higher and higher temperatures, the cross section, which is sort of basically like the probability that there is a fusion reaction, goes up accordingly. And for the most part, sort of fusion schemes have used isotopes of hydrogen. So all isotope is it's the same element, but it's just got an extra neutron in it, or one fewer neutron. And in the case of hydrogen, so the conventional hydrogen that we all sort of know of, in like H2O, for example, in water, that's protium, the nucleus of which is a proton. And then if you go to one heavier hydrogen, it's called deuterium, and the nucleus of that is a deuteron, which is just a proton and one more neutron. And then you can go higher still to tritium, but it's and the nucleus of that's a triton, one proton, two neutrons. Okay. And so most fusion schemes are trying to fuse these different isotopes of hydrogen. Now, cold fusion, basically the simple premise is, can you do fusion reactions at sort of low temperatures? And low temperatures is a relative term, so some of these fusion schemes are going to tens, even hundreds of millions of degrees. We're talking about sort of near room temperature, maybe 100, 200, whatever. And so, yeah, put simply, cold fusion or low energy nuclear reactions, which the acronym is LENR, or LENR for short, is the idea that actually in a metal, which, so let me back up here. So some metals can absorb hydrogen really easily. So like lead, titanium, nickel. And when they absorb hydrogen, they form something called a metal hydride. And so basically cold fusion, or LENR, is the idea that you can do nuclear reactions in a metal hydride of hydrogen isotopes.
Okay. Which produces energy that we can use, or hopefully could?
In principle, I mean, I want to be, I should also say from the outset that it's obviously a controversial subject. There's not a consensus at all. In fact, I would say the consensus is that this is not, the consensus is that this isn't possible. And the reason why is because, conventionally in fusion reactions, you need to get to certain temperatures in order for the cross section or the probability of fusion reactions to be noticeable. And so, but in principle, yes. I mean, like I'm working on this because I think that it could be a viable energy technology. At this point, though, we are very much at technology readiness level 0. So we have to actually prove demonstrably that nuclear reactions are indeed happening. And part of the reason why I wrote the piece is because I think like a truly dispassionate review of the empirical evidence suggests that, in fact, there are nuclear reactions happening in metal hydrides at low temperatures, but it's quite complicated, and there are a variety of issues, from sort of theoretical objections to issues of reproducibility. But I think sort of a deeper dive actually elucidates a lot of reasons why those might be the case.
Okay, so I have so many questions, it's hard to figure out where to go next. So I think I'm going to ask you like the two ones that are coming to my mind are like one about sort of the dream of cold fusion, and the other one is sort of like a social question about how it came to be a laughing stock. So I think I'm going to ask the dream question first. Like, okay, let's say these problems go away and there's a firm scientific basis for operating on this, and you go from level 0 to level 100, and we're there, right? So, dude, what's the dream? What are we going to do with this shit?
Yeah, I mean, so like uh, it's worth stating that, and I think I say this in the piece, that it's entirely possible that this is totally a real scientific effect, but it's
Hmm.
nothing more than a physics experiment,
Right.
and it will never sort of be a viable energy technology. Um, but I think it also totally could be.
Yeah.
Um, and so sort of functionally what this might allow you to do is influence sort of nuclear reactions from the get-go using material science as opposed to sort of relying on which kind of nuclear reactions you're doing.
Hmm.
And and so the way I sort of talk about it in the piece is I say it's sort of like nuclear react or cold fusion is like is to nuclear energy just as transistors are to vacuum tubes potentially.
Hmm. Hmm. Okay, cool. So, in other words, this would be a big level up if it worked. Like we would be, I mean, so one of the things that I like about Breakthrough is that you guys do a great job of talking about what energy allows us to do. And so what I'm hearing from you is that like it would basically turn fission as we understand it into a rung on the ladder or of on the energy ladder, and we would be unlocking new things with nuclear tech through cold fusion.
If this was demonstrated and accepted in the wider community, this would be sort of like a major nuclear revolution, I think.
Okay. Okay, cool. Well,
It's
that's
technological.
yeah, that's really where I wanted to go because like the transistor vacuum tube thing is like a pretty like that I think uh I mean that's basically the modern world right there. To give
Right.
people like a, a sort of a frame of reference for thinking about that, like that is everything from uh I don't know, man, like the step towards microchips eventually, like,
Right. Right.
at this tech to the electric guitar, like
Yeah.
that's to give you a suite of like what that would do. So this would be a similar thing in that domain if all the caveats that we've addressed here. Like that's the
Yeah.
dream.
And I mean, it would basically, to put it another way, it would allow you to do nuclear reactions with chemical level energy inputs. And so conventionally, these are thought of as totally different regimes. You've got sort of chemical or electronic energy states that are sort of on the order of like a few electron volts, say, which is the
Right.
unit of energy. Nuclear reactions are happening on the thousands or millions of electron volts.
Hmm.
And so conventionally, these sort of two domains are not thought to be able to be bridged together. But I think sort of the key insight is that conventionally when we're doing fusion, we're doing it at tens of millions of degrees. What happens at that temperature is that the atom is sort of ripped apart. You've got
Hmm.
electrons and the nucleus. The electrons negatively charged, nucleus positively charged, and they're ripped apart. And so you've got this like charged gas. And in that context, two nuclei that may or may not fuse are completely independent from another pair of nuclei.
Mm.
But in a metal, like in a metal hydride, pairs of hydrogen nuclei are not independent from one another. And so the reason why that's interesting is because you can get sort of collective effects where all of a sudden the normal dynamics that you're used to, if you're just looking at two nuclei sort of in isolation, it's not the same thing. And all of a sudden you can get an acceleration of these dynamics by quite a lot, depending on the situation. But basically, you're talking about nuclear reactions from chemical inputs, and it's interesting. The transistor sort of has interesting history here too. I think like most people, including myself for quite a while, um, just sort of thought the story of the transistor was in the late 1940s. Folks at Bell Labs, figured this whole thing out. They got a Nobel Prize, and all of a sudden, fast forward, I've got a smartphone,
Right, right,
etc.
right. Yeah,
Um,
yeah.
for several decades beforehand, before that 1947 discovery, there were sort of anomalous reports in the literature where people said they were seeing these amplification effects in the solid
Hmm.
state. But it was sort of like a little bit of a taboo, not very reproducible. Some famous physicists, like Pauli, for example, who's like a grandfather of quantum mechanics, he sort of he discouraged his students from studying it because, you
Mm.
know, and so there are sort of historical analogs here for solid, in particular, solid state technology and physics that has some trouble being reproducible for a while. We don't really understand it. Maybe even it's got a little bit of a taboo or sort of laughing effect. But then once we sort of figure it out, all of a sudden we're like, whoa, and you can inaugurate a whole new sort of technological wave.
So that's a great way to transition to sort of like, oh, how has it become this like laughing stock thing? And I want to get to that real quick, but I just want to point something out, right? So I generally have a more like philosophy background or whatever. And so the way that I understand what you're saying, the first time I'd ever really thought about this, maybe I should have thought about it before this, but the first time I had really philosophically thought about it was when I was taking a preceptorial on Hegel's Science of Logic. And he has an extended discussion about the relationship between quantity and quality. And so what I hear from you is that, there's this thought experiment where you like take a grain away from a pile, and at what point is it no longer a pile and it's something else, and that can be actually there are more sophisticated implications of what that means than we generally think. It's not just quantities, it's that the mathematical world that we interact with has a philosophical content of categorization that we deal with every day. And so when I hear what you're saying about, okay, we've got these sort of like high temperature fusion things, and then we've got these colder, lower temperature fusion things, and they live in separate worlds. What I see is that we're bridging the gap between a massive distinction that's being made between quality and quantity. And that when that happens, new potentialities, new categorizations, and new uh, praxes become available to us that we've never seen before. Is that
I
somewhat
think
right?
that's a great, yeah, I think that's a fabulous way of putting it.
Okay, cool. So now it's become somewhat more comprehensible to me. I'm down. I'm into it. Why shouldn't the DOE be throwing a little money at this? Come on. We want some long-term horizon stuff.
It's only
Tell me
$10
the
million.
story. Yeah, $10 million. Like, why not? You get a 10 million, you get a cold fusion, you get a cold fusion, everybody gets a cold fusion. So how did it become this sort of laughing stock? You talk about how the transistor experienced something similar. Walk me through the story here.
Yeah, so I mean, it's a complicated question, and I imagine it'll be the subject of a lot of philosophy of science in the
Hmm.
future. I think in general there I think in general, emergent phenomena that are sort of that meet two qualifications have trouble like this. And I think those are when you have something that shouldn't be possible, something that tautologically is inconsistent with the conventional
Hmm.
theory, and then something that has reproducibility challenges. And I think when you have those two things, it's a really good way to sort of dismiss, wrongly dismiss a scientific domain. And like I imagine a listener will sort of be thinking to myself, well, if it's not reproducible, then it's not real, right?
Right,
And
right, right.
all these sort of like just catchphrases of how science is done that people sort of latch on to,
Hmm.
and the thing is like actually from a historical perspective, that's not always true. Obviously,
Put
eventually,
some respect on Feyerabend's name.
but like, but like, obviously, sort of for scientific advancement to happen, you do need reproducibility. But
Sure.
but until you understand the theory behind a phenomena like this, then it does seem a little bit naive to expect reproducibility until you know all of the parameters that are at play. Because it could be the case that sort of you're doing an experiment. Some people see an effect, some people don't, but they're not fully characterizing or understanding their system, and so they don't know that actually the reason why someone else got an effect but you didn't is that they were playing with a parameter, maybe even without knowing it.
Mm.
For example, like with transistors, um, it was not sort of readily known at the time that you needed to actually like dope these semiconductors, which is just a term that means introducing impurities. It turns
Mm,
out that in semiconductors, impurities are actually critical. But if you
mm,
were sort of like a really well-funded laboratory trying to reproduce these amplification effects, and you didn't know that impurities are actually critical, then you might get the nicest sample, cleanest, and it would
mm-hmm,
work, right? So there are just sort of examples like this, and I think actually something very similar could be happening in the cold fusion realm. But so I mean, I think that's part of it. That I think sort of like philosophically, these types of phenomena struggle to sort of get mainstream adoption and struggle because it's genuinely scientifically difficult. I mean, I think that's one thing I want to emphasize here. This is genuinely a difficult subject to study. And when I was sort of first going down the rabbit hole on this, it was a genuinely difficult process to sort of make sense of the literature. And the reason why is because you have all these different experiments, many of which are sort of very high quality.
mm-hmm,
They were reporting, sort of what I call in the piece unambiguous nuclear observables. What I mean
mm-hmm,
by that is something like neutrons, neutron emission, or unnatural isotopic ratio. So I mentioned isotopes of different elements. On Earth, elements have natural isotopic ratios, and it's the same in Chile as in the US, as in the
mm-hmm,
UK. Um, and so if you see elements that have an isotopic ratio or distribution that is not natural, you know that you're working with a nuclear process because the only
mm,
thing that can do that is a nuclear reaction. And so that's what I mean by sort of unambiguous nuclear observables. But the difficulty is that you've got a range of different experiments stretching dozens of different laboratories over 30 years, but they show sometimes you see sort of patterns that are sort of similar between one experiment and the other, but in general, you just see this disparate set of results. Someone sees high energy alpha particles. Someone else sees new elements that appear to be like fission products.
mm,
And what that means is basically like if you do nuclear fission and you rip apart a heavy nucleus, you'll see lighter nuclei. And in a lot
mm.
of these experiments, you see new elements that weren't there before, only there after you do this experiment. And then you look at the new elements and you're like, oh, those actually like add up to the metal nuclei. Like
Right, right.
if you
Okay.
look at the masses, that they add up. It's like you don't have to be a rocket scientist to figure some of this stuff out. Um, but it's a genuinely difficult thing to sort of make sense of all these different results, and so it's very easy to dismiss this one and that one and that one because there's no sort of no common story. But again, and it's probably too technical to get into here, but for those technical readers, my article's full of links to some of these experimental reports and
Yeah.
also theoretical sort of explanations. And we you mentioned at the sort of at the top that I'm working on this Department of Energy project. So basically, for the first time in 30 years, the U.S. Department of Energy's ARPA-E, which is the Advanced Research Project Agency for Energy, it's sort
Mm-hmm,
of like the Department of Energy's DARPA program for the Defense Department. And for the first time in 30 years, they're funding cold fusion research. So they had a full process, 8 teams. I'm on one of them based out of MIT. And we've made basically a version of our grant manuscript available for anyone to read. So if there's,
mm-hmm.
fully open, if anyone wants to go check it out, I link to it in the piece. And that will sort of dig into, I think, sort of more of the theoretical explanations for why some of this might be the case and why it actually makes sense that we see a bunch of different types of results, which is very different than you would see from sort of conventional nuclear physics, where reactions tend to have very precise and consistent
Mm-hmm. Right. And by the way, everybody, you can check that stuff out in the show notes, along with your Twitter handle so that people can go and find you and pester you with questions about cold fusion. I hope they do because I think this is really, really fascinating. I'm so interested in the like institutional questions about science here. Like the how we come to quote unquote discover new things, like what is meant by observation, right? I
Yeah.
think you did a great job of sort of walking through that. And I bring that up because I think that there is, and this was my understanding for a long time, this basically naive understanding of science as both a method and as an institution, that they are A, one and the same, and that two, the method is, I think, stricter than history would actually tell you, which doesn't mean that you can just make anything up. That's not what I'm arguing. But that the process by which we come to discern, discover, and then implement these things is far messier than the received wisdom we get when we're sitting in our physics class in high school.
Yeah. No, that's a great question. Um, it really is. And it's funny because everything's sort of clear in hindsight.
Yeah, of
Um,
course. Yeah. 2020.
exactly. Yeah. But it's actually so much more complicated when these sort of quote unquote discoveries are happening. The other thing I think that I'll sort of say about discoveries is that like it is always also interesting how discoveries sort of get credited to like two people.
For
um,
sure. Yeah.
and
Yeah.
then without fail, you go back and look, and you're like, oh, actually, there's like probably like 4 dozen people we should be talking about when these things happen. Like one good example that's coming to mind is like, so Fermi for the first time back in the 1920s, I think it was, no, sorry, 30s, bombards a uranium sample with neutrons.
Hmm.
First time we did fission. The only problem was is his description of what was going on was not fission.
Right. Yeah.
That was quackery, right?
Yeah.
And in fact, Ida Nodak, who's sort of my scientific hero, she was this unpaid, because she was a woman, so she was an unpaid sort of
Mhm.
research helper, if you will, or something like that. And she basically looks at his paper and goes, um, I don't think that this is right. And then finishes her paper by basically saying, you know, I think actually maybe the nucleus is fissioning. She didn't use that word, but that's what she was
Mhm.
describing. And she was completely, made fun of. You name it. And then of course, like 6 7 years later, or something like that, everyone, oh, actually, you're right. Um,
Yeah, yeah, vindicated.
indicated.
Vindicated. Yeah.
Um,
Well,
and I suppose,
no,
but
go
just
ahead.
philosophically, I think there's another thing, and this is, I talked about sort of like phrases, catchphrases that are sort of
Mhm.
associated with scientific investigation. There's like this idea that like if you do an experiment and you get an unexpected result, it's probably because it's wrong,
Mhm.
and like that's usually true.
Mhm.
Um, and so it is useful to sort of have that disposition that like, okay, if I do an experiment and I get an unexpected result, it's probably because I made an error, and so I should go look for that error. But it's also possible you found something new, right?
Yeah.
Um, and so I think that there is like this instinct to out of hand reject things that are considered to be impossible from conventional theory. And I think
Mm.
actually, if you were to like press a lot of like hardcore skeptics about cold fusion, sort of like sit them down in a room, super technical discussion, they'd probably end up coming to something like, I think it's highly improbable or something like that.
Sure.
Um, right. And it's like, that's actually like a subtle difference that matters. Um, and I think like, and in fact, just to be clear, I don't think that the cold fusion research community is going to convince anyone of anything by sort of pointing to experiments from 20 years ago and saying, look at this paper, read this paper. I don't think that actually does anything.
Mhm.
Um, I think what you kind of need to sort of break the gridlock here is sort of like twofold. The first is you need people who are willing, who are sufficiently open-minded. They don't have to like, they can be deeply critical and skeptical. That's totally fine. But they need to be like sufficiently open-minded to sort of be ready for that kind of unexpected result. And then you need to have sort of like a credible evidence of anomalies. So
Mhm.
something that shouldn't happen, but it does. Here's the paper, we published in Nature or whatever, and then you can sort of have a discussion from there. So I think that's sort of like how we make progress here and sort of break this sort of gridlock or stigmatization.
Yeah. No, I think, well, that's sort of my hope for the new round of funding, that it will lead to new experiments that have can provide us with more fodder for making better decisions about what we think may or may not be happening here. I mean, I think that's ultimately salutary. And hearing you talk about am I wrong, or is there something new here? Right? Which I think is so hugely important, right? Because despite the fact that we credit discoveries to like two people, we auto institutionalize science
Yeah,
as this process that happens that away from human observation, specifically the observation of particular subjects who
yeah,
are engaged in observation, right? And so one of the most fascinating things that I've heard about this, there's a lecture from the 30s by Edmund Husserl, phenomenologist. It's called The Crisis of the European Sciences. And he makes a lot of fascinating arguments in it. It's been a while since I've read it, but I ended up reading he has an unfinished book length treatment of this idea. And I ended up reading most of it. It's the last parts of it are in draft form and kind of redundant, so you don't really need to read them, frankly. But he talks about this fascinating idea where he says, we have to understand that there is this like similar world that we're looking at, and that there is a phenomenological process in which we engage with that common world, and that all of the abstraction of science from that phenomena relies on that phenomena and the activity of perception. And that doesn't
yeah.
relativize the things that we get out of science, but maybe we ought to reground how we understand our relationship to these things. And then he says something very fascinating. He says, what's interesting about science is that it seems to stack on conclusions and abstractions to each other. And that can actually create a distortion in how we understand our relationship to this phenomena. And there's almost this like historical phenomenological process he describes as desedimentation,
No,
where you
interesting.
try to return yourself to almost this naive engagement with the phenomena. In other words, as I say at the top, I am not a stupid guy, but I'm a dumb guy. Be a little bit dumb almost, and
Yeah.
that you can actually re-enter older discoveries, perhaps in their own context, and reappreciate their implications in a different way that gets rid of some of the disembodied auto institutionalism and frankly unquestioned faith in the process that happens. And so when I hear you talking about this, I just thought you know, that seems so vital to how we approach this, that it is still experiments and it is
Yeah.
still observation, and that this is so crucial to humanizing science and understanding it as one of the human arts, which rather than putting it on a pedestal, puts it in a wheelhouse of things that we can share with each other.
That's beautiful. Yeah, I think there's a very healthy process, not just in science, but probably in a bunch of other fields too.
Sure, yeah.
Go back and say, all right, let me just re-question everything, or sort of let me just go back in time and sort of reevaluate. I think it's a perfectly healthy activity. Um, I think it's also worth noting that while sort of cold fusion or Leonard is definitely inconsistent with conventional nuclear theory. Another phenomenon, sort of you're going, I think, like sort of vertically, if you will.
Mhm.
There's a lateral move here too, which is to say, um, sort of my colleagues and I are sort of theoretical framework that we think explains some of these results. And it's not a complete theory, but it's sort of like a theoretical framework that starts to explain why you might have such a disparate set of results, or how fusion reactions can happen near room temperature at all. Um, and you can sort of make a lateral move here, which is to say, what are some phenomena that are like exploited, very commonly, well understood phenomena in other fields, in other
Mm.
fields of science that might actually apply here.
Mm.
So some of these collective effects, it's something called non-radiative resonant energy transfer, which is a complicated term, but it's basically just the idea that instead of giving off energy as particles, you can also give off energy in fields through field
Mm.
impact. And so anyone who works in solar cells or semiconductors, they'll know this as resonant energy transfer, which is a common thing in optoelectronics studies. So like this is you can apply these same ideas from you can make this lateral move, take ideas, concepts that are well documented. I mean, like this resonant energy transfer idea goes back to the 1950s. And it was actually applied theoretically to the nuclear environment in the
Mm.
60s. So, but you can sort of make this lateral move and say, well, this is a really neat idea from this other field that hasn't really been applied to, say, the nuclear space. Maybe we should do that. Maybe we should sort of look into that. And so I think there's actually two, at least for me, there's like sort of two ways of coming at cold
Mm-hmm.
fusion, sort of two motivations for why I think again a truly dispassionate, objective view of this space merits scientific investigation. The first is these anomalies. Like you can go back and read truly dozens of papers that are well controlled. They measure background. Like these are well done experiments. And then you see these anomalies that shouldn't be happening according to conventional nuclear theory, and yet they very clearly are. And then the other thing is sort of like a theoretical motivation, which was even if we had none of these anomalies, I
Mm-hmm.
actually think that there is reason to do to sort of study these types of collective effects in the solid state, but trying to sort of access nuclear energy levels purely on a theoretical basis. And you can sort of read more about that again in some of the
Yeah.
I linked to.
Yeah, no, absolutely. I mean, I love the idea of sort of the lateral and the vertical move here. I think that's really important. I mean, it makes me, I wish I had more time to read him, frankly, but I'm ever a student of Plato's. I'm fascinated by the problem of Socrates. And I was thinking about one of my favorite dialogues, which is the Meno, which is ostensibly by its opening question about virtue. It ends up being about epistemics. And the question
Nice.
that Meno asks Socrates is, can you tell me, Socrates, can virtue be taught or is it acquired by some other means? Which is a fascinating question, even in and of itself. But there are both vertical and lateral moves that are made in the dialectic of trying to figure that out. And the first vertical move that's made is, well, he says, you're already ahead of me because you seem to know what virtue is. So why
Uh,
don't you tell me what it is? And then he tries and he basically lists a bunch of things. And he goes, okay, so is it one thing or many things? And then you sort of go through there and it's like, okay, if we can't totally understand this as itself on its own terms, then what might it be like?
hmm.
Is it like this other thing? Is it like
Yeah.
that other thing? And that starts being the lateral move,
Yeah.
right? And that is basically how he brings Meno to understand that there's like uh perhaps some are better suited to education, types of education than others, and what that might mean. I mean, we don't have to endorse or agree with any of that, but that is a fascinating place to begin for a question about how do we even come to know anything at all. And so when I hear you sort of describe this, like, well, this is in this domain, maybe this is a way to create a new rubric to say, is this a mistake or is this new?
Yeah. Yeah. No, I think that's great. Um, and I think it maybe is worth sort of mentioning that, when I was sort of first introduced to this field, I was incredibly excited because I think it's
Mm-hmm.
an exciting thing. I mean, I think this is
Mm-hmm.
exciting stuff. But I was like deeply skeptical. This should doesn't make sense. Um, but when you see compounding anomalies, when you see like just dozens of papers, one after the other, that starts to just paint a super compelling picture. It still doesn't make sense, to be
Mm-hmm.
sure, but it starts to paint a super compelling scientific picture. And then you sort of, I get introduced to some of the theoretical work that's been done that starts to connect some of the dots. And again, it's still not complete, but I think it's one of these things where, like in hindsight, people will be like, "Oh, that made perfect sense."
Yeah.
Um,
Yeah.
and I think that will be a really interesting time if and when that happens epistemically. Why is it that it's so hard to see the obvious things when they're not quote unquote obvious?
Yeah, no, absolutely. That's a fascinating philosophical question too. So I don't think we can end it on a better note than that. This was a lovely conversation. I'd love to have you back on sometime about some other stuff. I'm sure it will come up. So thank you for making time to talk to me today, Jonah.
Thanks, Emmett. And I think I'll be seeing you at the Breakthrough Dialogue. Is that right?
That's right. I will see you next month. Yeah.
Looking forward
So,
to it.
everybody, remember, stay sharp, stay strong, and stay radiant. We will see you next time.